Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video, I'm going to give a quick introduction to all of the different parts of beam design in timber. So basically we're talking about, we have a member, timber wood member, and it's spanning some span, and it's supported on some kind of bearing support, and then we have some loads that are causing bending. And this is the very simplest case that I'm showing here, but we can of course have indeterminate cases as well, where we go across multiple supports, or we can have cantilevers like we're going to see in the example. And we want to be able to calculate the strength of this beam. Obviously, this is one of the key things that we want to do in structural engineering in timber. So we have a regular beam here, the bearings are shown in blue, and we have some kind of distributed load, and that could be any kind of distributed load that we care to evaluate it for. And when we design for bearing in timber, just like when we design for, bending, not bearing, just like we design for bending in any other material, we have multiple different failure modes that we have to check for. I mean, the most obvious one is bending causing failure, so moment, resistance, but we have a number of others as well that we're going to need to check. So there are 4 different parts of beam design, and in this video I'm just going to go over each of them one by one so that you know which ones we're going to focus on in the next videos. And then in the next video we're going to start to talk about bending strength. So the first one is the most obvious one for beams, which is the moment resistance. So we have some moment which causes tension in the bottom and compression in the top. What I've shown on the right is a wood member with pure moment. Now, of course, generally for beams, we don't typically have pure moment, especially when we're designing in timber. Usually we have moment combined with shear, so we don't get exactly this particular mode. We'll have some shear as well at the same time, and we're going to talk about that in a minute. But if we're just talking about moment, we are looking at, as I said, tension on one side, tension on the bottom, and we have compression at the top. And so the different possible failure modes are either tension failure in the bottom fibers, so actually have those fibers fail and pull apart, causing a split, which would cause the piece to fail. Or the other is that we could have a compression crushing failure on the top. So these are the ways that that we can fail for moment. And part of that compression part at the top, another thing that we need to talk about is going to be lateral torsional buckling, which is actually not the top crushing, but the top actually buckling out of plane. And that causes our member to effectively fail as well. And we're going to spend significant time when we talk about bending talking about lateral torsional buckling failure and how to calculate the strength of that. Okay, so the second potential failure mode that we have in timber is shear failure mode. So we need to calculate our shear resistance. Now, if you're familiar with steel design, you're probably familiar with thinking that shear resistance is not typically something that governs for steel, but if you remember back to concrete, shear resistance is a very important component, and it's the same deal in timber, but for a different reason. So in timber, when we have shear in our timber member, and this is my bundle of straws representing the fibers in a timber section, when I want to shear that, like by going like this, the straws want to move relative to each other in the longitudinal direction. Can you see that? So these straws are sliding past each other. And why this is a particularly weak failure mode in wood is because what's holding those fibers together, the fibers that are next to each other, what are holding these together from sliding relative to each other is actually the lignin in the wood matrix, and the lignin is the weakest part of the wood matrix. So shear is a critical failure mode that we need to check in wood, because it is easy to fail wood members in shear. And we have two types of shear. One is the longitudinal shear, which is the regular shearing like this, where all the fibers are kind of moving relative to each other. And the other one is called the notch shear, which takes into account problems that we can have if we cut notches in the piece of wood, causing stress concentrations that can cause it to fail. So if we're talking about longitudinal shear, we're talking about a failure at the place where we have the highest shear, which typically, if you remember your mechanics, would be in the center of the cross section, and we would have a crack form, and then that crack would propagate through the whole piece of wood, and the piece of wood would fail. For notch shear, what we're talking about is a stress concentration occurring in this reentrant corner notch. Why would we have a notch in a piece of wood? It might be common because of geometry to fit a piece of wood, or in order to set down a roof joist properly or something like that, to cut a notch in the piece to accommodate construction, and to accommodate if my piece of wood is otherwise too deep, I can cut a notch at the support so I can set it down a little bit further. But we pay a big price, we pay a big penalty for that, because if we do cut notches like that, it really weakens this section here for shear. And it's common that we can, because of that stress concentration, initiate a shear crack failure there at that point with a very low strength. So that is a separate check that we have to do in timber for looking at notches, which you wouldn't find in other materials generally. So the third mode that we have to check is bearing resistance, which we have covered in some detail already in this course. And this is a compression perpendicular to grain failure, which means I'm squeezing the straws. And as we discussed, this actually is a deflection criteria for considering failure due to compression perpendicular to grain. Of course, whenever we have beams, we need to sit them on something. So we're typically going to have some kind of bearing. I mean, the other option that we have, obviously, in beams is to cut holes like in a steel beam and bolt through. But it turns out that that type of connection is typically quite a bit weaker than a connection where we have bearing. That having to do with tension perpendicular to grain strength, which is very, very low in wood. So typically if we can bear a piece of wood, sit it on something in order to support it at the end, that is the preferred way to connect it to another member. And calculating the strength of this obviously is very important. And the failure mode is crushing of the fibers. And we talked about exactly how we can go about calculating that. So we're going to have to do that for every wood beam that we want to design. Okay, so the last one that we need to consider is deflection limitations. And this is, while the previous three failure modes were were ultimate limit state criteria, that is failure criteria, deflection limits are a serviceability limit state. And so we use different load combinations to calculate the loads to calculate the loads that we need in order to calculate deflections for checking deflection criteria. And for a simply supported beam like the one that I'm showing here, we would want to check, for example, the maximum deflection of the beam. That might not be exactly at the center, depending on where the loading is. But we need to calculate that deflection to make sure that it's not excessive. Excessive deflections are a problem serviceability-wise, so we don't want people in our building to observe the beams visibly deflecting under load, because that would make everybody uncomfortable. And even if the building is safe, strength-wise, under that condition, it is not going to be it's not going to be an acceptable design from the point of view of the occupants of the building. So that's why we need to consider serviceability. So those are the four things that we're going to look at over the next number of videos, with the exception of bearing resistance, which we've already covered, but we'll see in the examples how to calculate bearing resistance for beams. And in our next video, we're going to start talking about how to calculate moment resistance of beams.